So we've been talking about the behavior of electrons and how they act like waves and they act like particles. And we started talking about the quantum mechanical model of the atom and about how we can't really describe where electrons are, but we can kind of get this probability density or a density map of where these things are. So psi squared is the probability density, which means it's the probability of finding an electron at a given point in space. So psi squared is the probability divided by the unit volume. The s orbital is spherical, and what we see when we look at psi squared is that the probability density decreases as the distance from the nucleus increases. And that's fine. If we plot it, it resembles a multiple exposure photograph where you take a picture and you see the electron is there. And you expose the film again and you see it's here. And over time, you would get an increased density of dots in the center, and then out of that, not so much. What's important to remember, though, is that the electron is not moving around the nucleus like a moth around a flame or a moth around a light bulb, right? Just kind of flitting around. In a sense, the electron is everywhere within that probability volume at the same time. And that's a bit hard to get your mind around.
Is it everywhere because we don't know where it is? Or is it actually everywhere?
It's actually really everywhere. So we'll get to it, and hopefully it'll make a little more sense. So we can visualize an s orbital in this way, where this is more dense in the middle and it's less dense out here. And so there's a probability, I think they usually do these at 90%, that the electron is within this volume. If we graph the probability density, we see that it has a maximum at 0 distance from the nucleus, and that the probability decreases as you move away from the nucleus. That's a problem, though, because we know that the electron is not at the nucleus, and yet this probability density predicts that the highest probability is that the electron would be at the nucleus, and it's not. So we use a radial distribution function, and this represents the total probability of finding an electron within a thin spherical shell at a distance r from the nucleus. And this gives us a better picture of where the electron is likely to be found. So we've got this probability over unit volume. This has its highest value at 0 distance from the nucleus. And then we multiply it by the volume of the shell. So you take your distance from the nucleus and you imagine a thin shell at that distance. What's the volume? Well, that's going to increase as you move away from the nucleus. So we have two terms here, and they have opposite trends. And so what we end up with then, if we do radial probability, is we get a 0 probability at the nucleus, and the probability increases to a maximum and then falls off again. And this gives us a better method of deciding, where the electron is. The peak here for a hydrogen atom is at 52.9 picometers distance from the nucleus. And this is the same radius that Bohr predicted with his simpler model of the atom. And so that's a good sign, but it's important to remember that there's a very conceptual difference between these two ideas. The Bohr model says that the electron is always at 52.9 picometers. It's like a planet orbiting the sun, and the distance from the sun is always the same. I know that's not quite true because it's an ellipse, but in the Bohr model, they're spherical. Quantum mechanics says the electron is found at various radii, but 52.9 picometers is the most probable distance from the nucleus. Any questions yet?
Is there any pattern or anything to electrons' movement, anything like that?
Well, yeah, there is a pattern, but It's hard to understand electron behavior when we're only thinking of it as a particle. And that's what we're most comfortable looking at it as a particle. We can explain its behavior much better if we incorporate the wave nature of it. Question?
Does this pattern like help us then, like can we use that pattern to help us locate an electron all the time? Is that how we can lead to find it?
Well, does this help us locate an electron? No. It's going to tell us that the chances of finding the electron at any given point are greatest if you're looking at 52.9 picometers. But in terms of predicting exactly where an electron is at any given point in time, no, can't do that. So all of the s orbitals are spherical. The 2s orbital is just a higher principal quantum number, so it's a higher energy orbital. It's also spherical, it's larger, and so the average or the most probable distance from the nucleus for an electron in this orbital is going to be longer, and the 3s is larger still. But one of the things that's different is that the 2s orbital has a node in it, and the 3s orbital has 2 nodes in it. So a node is a point where the wave function goes through 0. And I've got a YouTube video where a guy makes standing waves with a string, and we can see this happening. So if you vibrate a string in such a way that you have, that the wavelength is 1 or half, so that the distance here can be divided by half a wavelength or 1 wavelength, you can set up a standing wave. And what we see here is that the wave travels down the string this way and it travels back this way. There are nodes at each end, and then there can also be nodes in the middle. And that's what's happening with the 2s orbital and the 3s orbital. We're getting a node in the middle. So let's watch the video, and then we'll talk about this some more.